All right, and welcome back to part 2 of the electric field video. We'll talk about ways to draw the electric field in this second part of the notebook video. So the first way to draw the electric field is to represent it as a vector field in which each point in space gets an arrow representing the electric field at that spot. Be aware, you can't show all the arrows because every point in space you just have a page full of black arrows, and large arrows can be difficult to show just because their length, they start to overlap with other arrows. So over on the right you can see we have a positive charge here because the electric field is going away. The arrows closer are bigger, and as the arrows get farther away they get smaller. On the right, we have a negative charge because the arrows are going towards it. Remember, the electric field is defined to point in the direction that a positive test charge would move. So a positive test charge is going to be repelled from a positive, attracted to a negative. So that's one way that you can represent the electric field, is through a vector field in which each point in space has a vector with a magnitude and a direction. The second way that we can represent electric field lines. Now, depending on how you put these stickers into your notebook, if you have the positive on the left, that's going to correspond to this diagram above. Negative on the right corresponds, and so these two diagrams would be essentially the same charge representation, but different ways of drawing it. Here we have the vector field, and down here we have field lines. You can see that these field lines kind of connect the arrows that we found up here. Now you can kind of see how those shapes are similar to each other. Here's some rules for drawing the electric field lines. They have to start on a positive and end on a negative, or go off into infinity, kind of like these ones are coming from infinity. These ones are going to infinity. The number of lines drawing a positive charge is proportional to the magnitude of the charge. So if you have twice as much charge, you should have twice as many lines going away from it. The density of the field lines represents the magnitude of the electric field. So closer to the charges, where we have more lines in a given area, the field is stronger. And out here where they spread out more, the field is weaker. The field lines will never cross each other, right? None of these lines cross each other at any point. And the field should be perpendicular to the surface of the charge, so they always have to originate perpendicular to the charge. We'll talk later about rules for field lines with conductors and insulators, but for individual charges, they originate perpendicular to the surface of the charge. So in these two diagrams, the charge on the left is stronger than the charge on the right. We can tell that because if you counted up the number of lines here, it would be greater than the number of lines here. And these charges have opposite signs because the field is going away from the charge on the left and the field is going towards the charge on the right. Here, the charges have the same sign. The charges are going away from both of them. Again, the charge on the left has more lines. Charge on the right, less lines, so less magnitude of charge. And there would be a spot right here in the center where the electric field would be 0 for each of these. Here we have what we would call an electric dipole. It creates kind of this melon shape. Here we have two positive charges. In the center it kind of creates this diamond. And at the very center, the electric field would be 0. And we'll talk about this more a little bit later. Here we have a conductor. The charges will be, or the field lines will be perpendicular 90 degrees to the surface of the. All right, so we're going to take a look at this example in which we have an electric field shown for 3 charges. Let's determine the sign of each charge. So for charge number 1, we see the field points away, which means charge 1 is positive because the fields always point away from a positive charge. charge number 2, the field also points away, which means charge 2 is positive. And down here for charge 3, we see that the field points towards the charge. And if the field points towards the charge, that means it's negative. The next step is to draw vectors at each point to represent the direction of the electric field. The electric field is always tangent to the field lines. So here, tangent to the field lines is going to be this way. Here, tangent to the field line is going to be straight up because D is at the cusp of the curve, so to speak. E, the electric field is going to be straight down. A over here, the electric field is going to be this way. And E, the electric field is going to be that way. And we should try to make these straight lines. Right? These are vectors where the magnitude represents the strength and the direction, the direction. Although I didn't do a very good job of representing magnitude with the length of the arrow here. Mark an X at the position where the electric field is 0. The electric field is going to be 0 somewhere in the middle of here, between those two positive charges, where the electric force would cancel out. If electric field is force per unit charge, the electric field will be 0 wherever the electric force is 0. Which charge has the greatest magnitude? Well, we should count up the number of field lines originating from each charge. Here we have 1, 2, 3, 4, 5, 6, 7, 8 field lines. That's going to be the lowest charge. And here, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 lines. Whereas for charge number 1, I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 lines. So charge number 1 is the greatest because it has the most number of field lines originating from it. At what lettered point is the field the strongest? Well, it's either going to be point C over here or point B over here. But because charge number 1 was stronger than charge number 3 because it had more lines going from it, point C is going to have a stronger electric field than point B because it's at least the same distance, if not closer, to a stronger charge. And when you're closer to a stronger charge, you'll definitely have a greater field. So C is going to have a greater field because it is closer to a stronger charge. In what direction would the force be on a proton if it was placed at E? Well, point E is right here, and a proton, a positive charge, goes in the direction of the negative field. So a proton would experience a force straight downwards. That might not be the force at some later time, but initially the force is going to be straight down. And then after that, it's probably going to get curved to the right, but initially straight down. Now at point D, which is up here, point D, we have an electron. And an electron goes the opposite direction of the field. So an electron is going to experience a force that is also down. We could say this one is with the field, and this one is against the field. It's a funky F. Field. All right. Now, for this example at the bottom, I will have a link to a PhET simulation on Canvas. But over at the right here, why don't you draw in 4 charges make them all positive, and I'll show you an example of how to use the simulation to get your field diagram, right? I made mine 3 boxes apart in each direction. Doesn't really matter whether you make yours 3 boxes or 2 boxes, but make it a square so they're even on each side. Let's go over to the desktop here. There's the FET simulation. We'll start that up. We're going to show a grid, and then I'm going to take positive charges. I'm not going to change the value of these charges. I'm going to put these charges 3 boxes apart from each other. And this is a vector diagram, but I can use this vector diagram to give me an idea of what the field diagram would look like. So let me switch back to my iPad. I have a picture of this already on the iPad, and here's what the field diagram would kind of look like for this charge distribution. I'm only going to draw 4 lines per charge. This first line is going to start going straight up, and then it's going to get deflected a little bit to the right. This line is going to start straight to the right, might get deflected a little bit up. This one straight to the right and maybe a little bit down. This one straight down and then a little bit to the left. Straight down and a little bit, sorry, that last one was a little bit to the right. This one's a little bit to the left. Straight over, a little bit this way. This line is going to come straight to the right and then get deflected up. And this line is going to go straight to the left and get deflected up. See how that's symmetric? This line, so one like that. And these ones kind of do the same thing. They will be symmetric here, right? Because we have a very symmetric charge distribution, we're going to have a very symmetric field diagram. And you should copy this diagram onto your notebook up here, right? It'll be something, oops. It'll be something kind of like that. And then this one. I think that's 4 for each, right? And they should start perpendicular to the surface. They should start perpendicular to the surface here, and then follow the pattern. And at the very center here, we would have a spot where the electric field is 0. So you'll put these 2 other charge simulations into the FET and draw your own electric field there. You can pause here if you want to do that, or do it later. Then we're going to look at 2 parallel plates here. This plate is going to be an insulator. This plate is going to be a conductor, and in between them we're going to have a positive charge. What are some rules for these situations? Well, for an insulator, the electric field can be at any angle to the surface. And the electric field can exist inside the conductor. And if the conductor, or if the insulator was charged, I could spell, that helps, C-H-A-R-G-E. If the insulator is charged, the charge can be distributed throughout. So it can exist all the way through. You can have charge in the middle, you can have charge at the edge, but that's only if the insulator has a net charge, which it won't in this case. It's going to be neutral. For a conductor, E equals 0 inside the conductor. Okay? That's when it's at equilibrium. The charge will reside on the surface of the conductor. And there is no net charge here when we're in equilibrium. And the conductor will be polarized in presence of a charge. All right, so because we have a charge in the middle here, it's definitely going to be polarized. So we know the electric field goes away from a positive. So it's going to go away from a positive, it's going to go right up through the insulator, because an electric field can go through the insulator. The conductor, it's going to go to the surface of the conductor. It needs to be 90 degrees, and then it's going to continue on the other side, but it's not going to exist inside the conductor. This field line comes straight off, 90 degrees, then it continues this way. 90 degrees, then it continues. And the ones that come straight out the side here are probably going to be attracted to that conductor because the conductor gets polarized. So it'll be something like that, roughly. All right. Here we're going to look at the electric field for a point charge in a conducting shell. So this shaded area here, that's a conductor, and the plus is our point charge, and we're going to draw another one of these over to the left. I'm going to put a plus there, that's my point charge. This one I'm going to make symmetric. So I'm going to kind of count out maybe two spots out, and then another spot beyond that. And then I'll draw some concentric circles here. Okay, so there's our conducting shell. Kind of shade that in. And what's our electric field going to look like? An electric field goes away from a positive. It's just going to go straight away from it. It's going to be perpendicular to the surface of the shell. This shell will become polarized. It's going to be negative on the inside because the electrons get attracted to that positive on the inside, and the shell is going to be positive on the outside, and electric field points away from a positive. The electric field will be 0 at the center of the shell or inside the shell, because inside of here there is no electric field at equilibrium. We'll talk more about that later. In both of these cases, the conducting shell is polarized, and the field, the electric field, will be symmetric outside the shell unless other charges are near. Okay. So on the right side, we're still going to have the field lines being perpendicular to both of these surfaces. However, we're going to have to do some curving here in order to get this field line to be 90 degrees there. 90 degrees. I drew one here, 90 degrees. 90 degrees to both of them. This one will just come straight across. And then on the outside, the field is going to be symmetric. Right? So it's not going to match inside to outside. So the outsides of these two should look the same. Out here should be the same as out here, but inside is not going to be the same. This conducting shell provides an insulating barrier between the outside and the inside. So even if the inside is not symmetric, the outside will be symmetric because it's insulated from this inner charge, because in here we have no electric field.